Well, hello everybody. So today we'll begin talking about something called a definite integral. Okay, and I'll start the video with part one to tell you a little bit about some vocabulary and the concept behind a definite integral. Okay, uh, and beyond that, let me start by contrasting two things. Now, this right here, these two examples, we've seen that type of thing before. These are indefinite integrals, okay? And what does it mean to evaluate an indefinite integral? It means you find the antiderivative, okay? And you put plus c, where capital C is some unspecified constant. So in other words, if I have this function 2a right here, so capital A is my variable in this indefinite integral, then the antiderivative of that is a squared plus c, because the derivative of a squared plus any constant is 2a, right? So that's what an indefinite integral is, and that's how we evaluate it. Same thing with this other one. What's the antiderivative of 2 times e to the power 2x? It's e to the power 2x plus c, okay? That's the antiderivative. If you took the derivative of e to the power 2x plus any constant, you would get this thing over here, okay? Now, for different problems, there might be a slightly different technique or a different rule for how you find the antiderivative. And I've covered the techniques and the rules in other videos, but that's what indefinite integrals are. Now, we're talking about definite integrals in this video, which is a new concept. So here is a definite integral right here, okay? And it looks the same for the most part as the indefinite, except for there are these numbers. So this like elongated S right here, this is the integral sign. It's part of notation in calculus. You notice that there's a number at the bottom and there's a number at the top. Okay, all right, that's a definite integral. This number at the bottom is called the lower bound of integration, and this number at the top is called the upper bound of integration. All right, now, so that's what it is. It doesn't look that much different, okay? What I haven't told you yet is how you would evaluate this and what we use them for, okay? But that will come. Just for now, I wanted to say that there's this thing called a definite integral, okay? It looks kind of like something we already know about, an indefinite integral, but there are these numbers included with it. The bounds of integration, the lower bound of integration, and the upper bound of integration. You still have a function in here. This time the variable is lowercase r. The function is r squared, okay? You still got that. Uh, but, otherwise those numbers are what makes it different. Okay, so that's what it looks like, and that's some of the vocabulary to go along with it. So part two, it's like, how do we evaluate a definite integral? In math, we evaluate, we calculate, and so on. So let's talk about that part. It's maybe not that difficult. I mean, it might vary by problem, but I can tell you how to evaluate a definite integral in a very straightforward way. You just use the antiderivative. Well, let me show you. So let's take this example that I've just mentioned. See this one where the function is r squared, okay? And the variable is lowercase r. So here's what we do to evaluate this or potentially any other definite integral. We find the antiderivative of r squared, okay? And that would be r to the third power over 3. Okay, we find the antiderivative. Some fine print about that, we leave out the constant of integration. So yes, antiderivatives do, you calculate them with whatever rule is applicable, and then you put plus capital C, and that capital C is some unspecified constant. It's called the constant of integration. Well, when we evaluate definite integrals, we use the antiderivative, that's true, but we leave out the plus C. Okay, so step one, I find the antiderivative. There it is. And I'm going to put it in these brackets with the bounds of integration along with it. So there's the lower bound of integration, which is 0 in this case, and the upper bound of integration, which is 3. Okay. Then I take that antiderivative, I plug in the upper bound. See, 3. What's that going to look like if you plug it in there? It'd be 3 to the third power over 3. Take that upper bound, plug it in the antiderivative. then you subtract, and then you plug in the lower bound, which is 0. So what's it going to look like if I put 0 in there? It would be 0 to the third power over 3, which you see right here. So we plug in the upper bound, we write a subtraction, and then we plug in the lower bound, and then we just do that calculation. And we'll get 27 over 3 and 0 over 3. We'll get 9 if we do that. 9 is the final answer. Okay? So that's how we can evaluate a definite integral. We use the antiderivative as outlined right here. Now, as a disclaimer, there are other ways to evaluate definite integrals besides what I just showed you. But this will be a reliable way for us to do it. And it's called, this method right here of evaluating a definite integral is called the fundamental theorem of calculus. All right, so if that comes up in a question, if you run across it, it refers to this technique, this particular method of evaluating a definite integral. There are other ways to do it, all right, but this is the way I'll focus on in our class. So okay, let's take stock where we are. What I've told you so far is what a definite integral looks like, what the upper and lower bound of integration are, and now I've told you how you can calculate it, all right? But how about this? Before I tell you anything further beyond that, let's look at another example of calculating or evaluating a definite integral by the fundamental theorem of calculus, meaning with the antiderivative, okay? All right, so here's another example. Look at this one. It's here's how we might read this. We might say the definite integral from 1 to 9 of 40y root y plus 6 root y dy. So lowercase y is the variable. There's my function. Okay. Now because this problem is more complicated, I'll break it into steps. So step 1, I'll need to find the antiderivative, because remember what you do is you find the antiderivative of whatever that given function is, and then you plug in the upper and lower bounds and subtract. Okay, so I'll need to find the antiderivative, and to do that I need to use like a rule in the correct way. Okay, so for when I'm looking at this type of thing and I see root y and y, then I'm thinking that my rule is going to be this one. There's one of our first rules that we learned. It says the antiderivative of x to some power n is x to the power n plus 1 over n plus 1 plus capital C. So that's the rule that I see being applicable to this. But notice how like that doesn't say you can have x to the a power times x to the b power. It doesn't mean you can have like the variable y, but then times the variable y again to some other power. It's you've got your variable, whatever it is, x or y or whatever, and you have a power. So see how there's the y and the root y right here? So that y to the 1/2 power, as I rewrote it, that's root y. I need to combine that into a single variable and a single power. So we can do that this way. There is a rule from algebra that says when we multiply like things, like variables, we can add their exponents. So y to the first power times y to the 1/2 power, I just need to add 1 and 1/2. So that'd be 3 over 2. So this will be 40 y 3 over 2 plus. Now here I don't have a problem with that one. That's just y to the 1/2 power. So I'll leave that alone. All right. Okay. Now, when I have it that way, right here, you see like this, got 40y power 3 over 2 plus 6y power 1/2. Then I will use my rule. I'll add 1 to the power, and I'll divide by whatever it gets. So 3 over 2 will become, if I add 1, that'll be 5 over 2, and I'll divide by 5 over 2. And 1 over 2 will become 3 over 2 if I add 1, and I'll divide by 3 over 2. Then I'll do some calculations. If you take 40 and you divide by 5 over 2, that turns out to be 16. And if you take 6 and divide by 3 over 2, that turns out to be 4. Okay, so here is that thing that I wanted, the antiderivative, which I'll abbreviate AD. Now, that's the whole key to evaluating this definite integral, remember? So I here I'll evaluate it with the bounds as I mentioned. So I write the original problem again. You don't have to do that, but I'm doing that for you. Okay, this is what we got. We take our antiderivative in preparation to put our lower and upper bound in. Okay, and then what? I put the upper bound in first, and I put the lower bound in second, and I subtract what I get. Now, I wrote this one out with different colored pens because I wanted you to see something. So notice, if I take 9, that upper bound, and I put it in here, it'll be 16 times 9 to the power 5 over 2 plus 4 times 9 to the power 3 over 2. Then I subtract, but that subtraction has to apply to everything that comes after it. So notice I put these parentheses there to group everything together. So here's what I get when I put in the upper bound and then minus parentheses. That's what I get when I plug in the lower bound. So I'll just do that because I don't want you to think if you were working this on your own that subtraction would only apply to that next number that came after it. It applies to all of this. So if you wanted to calculate this one number at a time, this subtraction would have to distribute to everything that came after it, okay? Whenever you put in the second bound. Now, as I did it, I just calculated these numbers individually, and here I got 3,996. And between those two, I got 16 plus 4, 20, and I didn't have to distribute the subtraction. But if that ever comes up, okay, that subtraction must apply to everything that comes after it, if there's more than one thing. Okay, so that's how you would handle it in that case. Here, I get 3,996 minus 20. If I just calculate all those numbers down to the very end. Final answer, 3,976. Okay. And then I'm done. I've evaluated the integral. Now, so to do this, you maybe know most of what you already need to know, because I guess beyond this step here, which is just plugging in my bounds and calculating, that's just arithmetic. That's something that we can do with a calculator, right? The only other part is finding the antiderivative, but that's something that we've been working on already leading up to this point. All right, so what have I told you so far? Let's take stock real quick. So definite integrals, here's what they look like. They have an upper and lower bound, okay? Then I told you how to evaluate one. You use the antiderivative in this certain specific way. All right, I gave you a little bit more complicated example to follow that one. And then last thing is, what can we do with a definite integral? Okay, so that I haven't told you yet. I've just showed you what it is and worked an example or two. One thing that we can do, well, first of all, there are so many things that we can do. It's a very important tool in math. Integrals are. So, but one thing that I think would be relatable is that we can measure areas, okay? And so here's how. If I have a curve, say I have a graph, this is the x-axis, this is the y-axis, f of x is some function, and here's the graph. Say I mark off a space from number A to number B on the x-axis, above the x-axis, but below the curve, okay? It's called the area under the curve. You can search area under the curve on the internet and find all kinds of stuff about calculus and so on. All right, so that area, which is irregular, it's not rectangular, it's not triangular, it's not circular, like there's no formula for how much space is here, and measuring the area is just a measurement of how much space is there. That area can be calculated by this definite integral. It's the definite integral from A to B of f of x, the function for the curve dx. All right, so yeah, it can measure that. Definite integrals measure areas. They also measure volumes and all kinds of things beyond that. But I was going to try to tell you something fairly simple that a definite integral can do. Let me show you something from one of our assignments, okay? So this is from the assignment that I'm making this video for. It says, calculate this definite integral but use the interactive figure to find your answer. Okay, so sure, I can work things out with pencil and paper like I've showed you so far, but it's definitely not hard to do it with technology either. So let's see. Here's a picture kind of like I've just showed you, all right? And it's got a curve, okay, and that's the graph of this thing right here, okay, that we started with, x to the third power 3 minus 2x squared. You know, if you were to graph that, it looks like this. And I want to do the definite integral from 0 to 6. So I can adjust my bounds right here. So I'll adjust this one to 0 and this one to 6. And notice how it covers a different portion of the area under the curve and above the x-axis. Okay. All right. So I've got the integral, but I'll go ahead and click area here, and it tells me the area is 48. So that's how big this space is. If we were measuring in feet, like if this was some giant graph and this was 1 foot and 2 foot, this would be 48 square feet. That's how big it would be. The answer to this definite integral tells me that. It tells me the area. All right. So it's told me that I didn't have to do any work to figure that out, but I've conveyed to you that that is what it tells me, and also serves as an answer to the integral. Okay. All right. So sure, we can use technology sometimes. Sometimes we might need to work things out on paper, right? But now you know something, some application that you can attach to a definite integral, the area under the curve. I'll talk more about that in additional videos, okay? Another thing that we will probably do is calculating the consumer surplus. So what I decided to do was go to the Wikipedia page on economic surplus, and already you see like a graph. It's got a demand curve and a supply curve, and there's this kind of like what I was just telling you. There's a portion of the area under the curve that's marked off that's called the consumer surplus, and then there's another portion that's marked off as the producer surplus. Now that's not exactly what I was just showing you with the area under the curve, but you know, it seems to be going in a similar direction. But anyway, here we look around and we see what? Now you might not understand this article, you might not understand everything that's involved in it, but at least for right now, if I was going to try to tell you that definite integrals are very common tools in mathematics and all the disciplines that use math, like economics, chemistry, physics, and so on, then what do you recognize that to be? That's a definite integral, okay? There it is. That's what we're looking at right there as a definite integral. Okay, so they are very useful. You'll see them all over the place if you continue doing math or anything that uses lots of math. Okay, so with other videos, I will show you more about the applications, but for now, we know about the applications, and we know what a definite integral is, and we know how to calculate it.